In this physics lesson, we'll be talking about electromagnetism. In the previous lesson, we were talking about magnetism. So right now we are studying electromagnetism. So by just looking at the word, what is electromagnetism? So it's made up of two words, which is electricity and magnetism. So it's just a topic which tries to study the relationship which exists between electricity and magnetism. So we are saying it is the process of producing magnets by using electric current, or simply saying by using electricity. So when current passes through a conductor, it induces magnetism in the conductor. From there on, we should understand this statement which is saying when current passes through a conductor, it induces magnetism in the conductor. By having a look at this experiment, where we're saying to show that magnetic fields are created around the current carrying wire. So previously, I stated that whenever we're having a wire which is carrying current, there will be a magnetic field which should be produced around that particular conductor. So in this setup, you arrange the materials like this one, whereas you have this one is just a conductor passing through a cardboard. So this is a conductor passing through a cardboard. So on the cardboard, forget these lines, you press compasses. So you can press one or two, three, four compasses for a clear view, but even one is just enough. So this is how you arrange them. So here having the switch. So when you close the switch, or before you close the switch, observe the direction of the what of the compass needle. So it has a needle or a pointer which is inside. So observe that particular pointer. So the way these compasses work is that they gets interfered when they are brought closer to what to a magnet, or when they are brought closer to a magnetic field. So we use compasses here just to detect the magnetic field produced. So if the compasses will deflect in one direction or point in in another direction, it will mean that there is a magnetic field which is produced around it. So close the switch and observe what will happen. So when you simply close the switch, you observe that the compass deflects or changes its points in another direction, simply showing that there is a magnetic field which is being produced around around the conductor. So you can place several compasses so that you clearly observe the direction of the magnetic field. The magnetic field has direction. So how do you find this direction? We don't guess in physics or in sciences, so we do experiments. So we understand them later by looking at some other laws which we use to determine the direction of this magnetic field. So we're saying when there is no current, there is no deflection, as I've said. In reversing the direction of current changes the direction of the pointer. So which means you can change the direction of the magnetic field by simply what? By simply reversing the direction of the current. So now how can you increase the strength of electromagnetism? As I have said, electromagnetism is the process of producing a magnet by using what? By the use of electricity. So the strength of an electromagnetism, it means that that magnet is made by what? By electricity. So how can you increase the strength of an electromagnet? So you can increase the strength by increasing the amount of current flowing in the circuit. That's the first way. So which means by increasing the amount of current in the circuit, you also increase the strength of the what? Of the magnetic field which should be produced around it. Hence, the strength of that particular electromagnet. And again, by increasing the number of turns in a solenoid. Previously, we have discussed what a solenoid is, and placing a ferromagnetic material inside the what? Inside the solenoid. So by doing so, you will increase the strength of an electromagnet. Now let's have a look at the laws which are used to determine what? Laws which are used to determine the direction of the magnetic field. So the first one we have the Maxwell's corkscrew law. So the direction of the screw is the direction of current, whereas the direction of the motion of the thumb gives the direction of the lines of force. So imagine holding or using this screw or the operation of this Maxwell's corkscrew law. So this law, you imagine by using this law, whereas when you are screwing this law, it means you are pushing it down something or you're pressing it down something. So if you are screwing, it means that the pointer will point the direction of what of the current, whereas the direction of the screw when you are screwing, it will show the magnetic field. So that's about the Maxwell's corkscrew law. In the other important law, we have the light hand grip law, which is easier to use than the imagine the microscope solo assist. Sometimes it's tough or hard to imagine. So the right hand grip low, it simply uses the what? It simply uses the hand. Whereas you imagine using your right hand holding a conductor. Whereas the way you hold the conductor should be that the thumb should point the direction of electric current. So when the thumb points in the direction of the electric current, it means the rest of the fingers will what? Will point in the direction of the magnetic field. You can even try on this further picture by simply using your right hand. You simply show that these fingers will point in the direction of the magnetic field as simply shown. So this is in a straight current, in a straight wire carrying current or a straight conductor. And again, you can have this situation where you can have a solenoid. So in a solenoid, this is how you use the right hand grip view to show the direction of the magnetic field. We also have the loop. So in the loop again, you can simply apply the right hand grip blue there. Then you see that the direction of the magnetic field will be like this one. So this is how you determine the direction of the magnetic field by simply pointing your thumb to the direction of current. From there on, let's look at one of the most important things about this topic, which is force on a current conductor, also known as the Mora effect. So this part clearly states that when current flows in a conductor, it produces magnetic field. When this conductor is placed between two bar magnets, it moves because the magnetic forces interact. Let's have a diagram there. So yeah, we can say it's an experiment. So imagine pressing a what? Pressing a conductor carrying current. We have discussed that whenever a conductor is carrying current, it produces magnetic field around that particular conductor. Then here we are pressing it what? Between two permanent magnets having opposite poles. Here having south pole, here having north. So it means there will be a magnetic field should be produced between these what? Between these permanent magnets. So since the current carrying conductor you also having a magnetic field. So the magnetic field of the what of the bar magnets and that of the what of the current conductor, they will interact. So the interaction causes a what causes a force on the current conductor. Hence the current conductor it moves. That's how this one works. So you simply place a conductor carrying current on the what between two permanent magnets. So it will produce what? It will produce a magnetic field. So because you are placing it between what? Between another magnetic field. So the magnetic fields they do interact. So the interactions makes the what? Makes the conductor to move in one direction. So the wire might either move up or down simply because it expresses the force due to the magnetic field it produces and that of the magnets. The interactions is the one which makes them to move, as I have just said right now. Then you have this other important law, which is the Fleming's left hand law. So what is the Fleming's left hand law? So this is just a law that is used to determine the direction of motion, magnetic field, and the direction of current. And it states that when the thumb and the left two fingers of the left hand are held at right angles to each other, the first finger points to the direction of magnetic field, the second finger points to the direction of current, and the thumb points the direction of motion. You don't have to memorize all that, but you just simply know how to use this Fleming's left hand law. So this is the Fleming's left hand law. So you imagine the conductor like this one. So if the thumb and the first two fingers of the hand are placed at right angles to each other, the thumb will point the direction of what? The direction of motion. The first finger direction of the magnetic field. The second finger direction of current. So you might wonder how to use this Fleming left hand law. So what's the key thing here? The most known thing on the left hand is the direction of current, right? So just place them in the way as this image is showing us. So make sure that the second finger should point the direction of current. So when you lock that finger in the direction of current, it means the other fingers will point the direction of the magnetic field, and the thumb will point the direction of what? The direction of the force which is produced or induced on the particular conductor. Now we are moving into the applications of electromagnetism. So what are some of the applications of electromagnetism? First of all, we start by discussing the Mora effect. So what is the Mora effect? is the experiment we just did on investigating the effect of pressing a current conductor onto a onto two permanent magnets. So the first application is the electric motor. So it is the device which uses electric current in a magnetic field to cause a rotation. So how does it work? So this is an image of what showing how the an electric motor works. So we're saying when the switch is closed, current flows through the coil and produces magnetic field, as you have discussed already. The magnetic field produced in the coil, which is that of the current conductor, and that in the permanent magnet, they do interact. So the interaction of the magnetic fields, which is that of the permanent magnets and the what and the force and the current conductor, pushes the sides of the coil, making it to rotate in one direction. But when it's rotating in this vertical, we say that it's not cutting any lines, but due to its inertia, the inertia carries it and continues to move forward. Hence, the motor keeps on rotating and the motor effect. So what happens is that we're having this conductor carrying current and the space between two permanent magnets. So it produces a magnetic field, and this permanent magnet again produces another magnetic field. So what happens is that the magnetic fields here, which are on this particular place, they do interact. So it is this interaction which makes the conductor to express a force, the magnetic force, that is to say. So the force makes rotate the conductor to rotate in one direction. But when it stops vertically, it doesn't carry it doesn't carry any magnetic field lines. So these magnetic field lines are not cut or they do not interact at vertical position. It means what? It means there won't be a force on the conductor. But since it was moving before, its inertia will carry it forward. Hence, it will slightly bend at an angle and it will carry some field lines which will again make it to rotate. Hence, it keeps on rotating up until when the DC power is removed. And here, how can you increase the speed of rotation of the coil? You can increase the speed of rotation of the coil or the motor by simply increasing the current, which means you strengthen the what? You strengthen the magnetic field produced by the wire by increasing the number of turns, which means you increase the number of what? The number of magnetic field lines of the permanent magnet should be cut by the conductor. And again, you increase the what? You increase the strength of a permanent magnet so as to increase the speed of rotation. And increasing the area of the coiled wire, which is just the same as increasing the number of turns of the coiled wire. Another useful application of electromagnetism in everyday life is the electric bell. So how does this electric bell works? So the electric bell, let's look at the image. The electric bell works in such a way that let's discuss the past phase. So here having the gong, here having the hammer, right there having the software and the matcher, there having a spring, they are having the cell with the power source, they are having the switch, then they're having electromagnets. So which means they only become magnets when current is passing through them. And they do not behave as magnets when there is no current. So how does the electric bell works? So one has to place the switch to close the circuit. So when the circuit is closed, so there is current flowing throughout the conductor. And again, this is a part of the conductor. In all of this one again is a conductor. So when current flows through the circuit, the electromagnet becomes magnetized. So what do you think happens? They do attract this soft iron armature. So when this soil iron armature is attracted, the hammer on which it is attached to, it hits the gong. So when it hits the gong, you observe that here we have the contact, and when this one is attracted to the other side, the circuit will break, which means like it's like the contact has breaked. It's like there's no contact between the software armature in the part of the contact. So which means the circuit becomes incomplete. Hence current stops flowing through the conductor. And the electromagnet becomes what becomes demagnetized. Hence the software armature is no longer attracted and tends to come back to its original place with the help of the spring which is there. So when it just reaches the contact again, it's like it makes the circuit become complete. In the process, repeats itself, whereas the electromagnet will get magnetized again and attract the software armature, making the hammer to hit the gong. hence putting the contact apart, and the software matcher will go back, and the process will repeat itself as long as the switch is still closed. That's the basic operation of an electric bell. And again, you have a moving coil loudspeaker. So in a loudspeaker, you also have magnets inside them. So what are these magnets made of? You have permanent magnet and an electromagnet. So how does it work? We are having a cylindrical magnet there. Then you have magnetic field lines. Then you have the movable coil. Then you have current. We have wires from the amplifier. So these wires, we have two magnets here. We have permanent magnets, which is the cylindrical magnet, and the one on the middle is the electromagnet. So what happens is that when the AC is passed through the movable coil, so this is the movable coil, it creates either forward or backwards force on the coil. The forward or backwards force of the coil causes the diaphragm, which is practically there, to vibrate, and the vibration creates sound which travels through the sounding air. So how does this actually work? We're having these wires from the amplifier. So the amplifier strengthens the signals of the what of this audio or the sound. So when they are reaching there, since you're having AC power, so AC is alternating current, right? Which means the magnetism which will be induced into the coil will also be changing or varying depending on the what, depending on the strength from the amplifier. So which means the alternating magnetic field will create alternating magnetic attractions. So which means the diaphragm will be attracted differently depending on the what, depending on the strength of the signal which is produced by the amplifier. Hence the vibrations will differ, the what, the wavelength and all the other factors which are there for sound to travel will differ. Hence making the sound to be heard to the what, to the ear in a different way. That's how sound is produced by a moving coil loudspeaker. Another application is this is a magnetic relay. Forget the moving coil loudspeaker. So it's a magnetic relay. So it is a switch which uses an electromagnet produced from the first switch. So how does this work? Let's look at the diagram. We're having the first circuit and the first switch. So which switch do we close? We close this switch actually. Then you're having an electromagnet. It becomes a magnet only when the switch is closed. We're having an iron armature. Definitely should be attracted to the electromagnet. Then you have the second switch. So how is this second switch triggered? Let's see how it works. So when the first switch is closed, the electromagnet it becomes magnetized. Hence it attracts the what? It attracts the soft iron armature. So when this one touches the electromagnet, it means it still stays there as long as the switch is closed. So when this attaches to the electromagnet, it's like the circuit is complete. Hence, current the second switch conducts current, hence powering up when any output which may be placed outside there. So we're saying this attracts and pulls the iron armature, which causes the second switch. Hence, when the second switch closes, current passes through the what? Passes through the second switch. So it's just like a switch which is used to what? To control the time it will take for the other switch to what? To be turned on. So let's say the electromagnet, we pressed a hard magnet inside it. So it's like a solenoid. Like a solenoid. So we press the one, we press maybe steel inside instead of iron. So which means if you press steel, it will take a lot of time to be what, to be magnetized. Depending on it also varies depending on the current. So it take a lot of time to be magnetized, which means it will take a bit of time when the first switch is closed for the second switch to start what? To start operating. Reaching this far, we are done with electromagnetism. So see you in the next video where we'll be discussing about electromagnetic induction.